Okay, equilibrium. We're at Chatliers principle. Let's see what we can do. Chemical equilibriums are conditions under which reactions go to completion. We're going to define chemical equilibrium. We're going to write chemical equilibrium expressions and carry out calculations that involve them. We're going to explain the nature of equilibrium constants. So let's get going. Reactions that go to completion. Reactions that go to completions are those whose reactants are completely used up and only the product remains when the reaction's over. Single arrows indicate the reaction that goes to completion. It only goes one way. The arrow points to the product, that's the end. Just like this. Okay, a reversible reaction is one that can go both ways. We have some reactants form products, then the products react to form the reactants, and they go back and forth and back and forth. We use arrows that go both ways. Sometimes you'll see a smaller arrow going one way and a larger arrow going the other way. That just means it favors the one direction. The reversible arrows are read as in equilibrium with. That means the reactants are in equilibrium with the products. Sort of like a teeter-totter that's stuck. To define chemical equilibrium, it occurs when a reversible reaction, when the rate forward is equal to the rate reversed. Now we're going to do a lab in class that has to do with this. Again, the rate forward is equal to the rate reverse. To start writing an equilibrium expression, we start with a balanced chemical equation. So this is just a generic chemical equation. We have the smaller letters here represent the coefficients that we use to balance the equation, and the bigger letters, or the capital letters, represent the compound. So, to write an expression, what you do is products divided by reactants. Take the product to the power of its exponent, or power of its coefficient. See how the products are over the reactants. These brackets here represent molarity, which are moles per liter, a concentration. So moles per liter. What goes into the expression? Solids do not go into the expression. So if you have a solid, it just drops out. If you have a liquid, just drops out. If you have gases, they do go in. If you have aqueous, dissolved in water, it goes in. So we start with a balanced equation. We write our expression. Then notice the states. Here we have aqueous, that stays in. Solid drops out. Okay? And liquid here would drop out. So C and B are gone. The final KEQ for this reaction is just this, because the liquid and the solid are not part of it. What is the meaning of KEQ? Well, if I get KEQ and it's greater than 1, that means the products are favored. If I get a KEQ and it's equal to 1, that means the products and the reactants are equally favored. If I get a KEQ less than 1, the reactants are favored. Excuse me. So shifting chemical equilibrium. This is things that can disrupt the equilibrium, make it go one way or another. Common ion effect. So let's talk about Le Chatelier's principle. It's a shifting one side to another. That's why all the teeter-totters. If a system at equilibrium is subject to a stress, the equilibrium will be shifted in the direction that tends to relieve the stress. So if I push up or down, it goes to relieve the stress. The system is chemically or physically changed. Whoops, let's go back. Stress is any change in pressure, temperature, or concentration of the system at equilibrium. So I've reached equilibrium, now I'm going to put a stress on this system. Let's talk about 3 factors that disrupt equilibrium. First is change in pressure. Pressure change only affects reactions where the reactant and the product are all gases or part gases, where they're not equal, where one side has more gases than the other side. So we also have change in pressure. Change in pressure accompanied by an increase in the volume will decrease the pressure. When pressure is up, the shift is towards the side that has the least moles of gas. When the pressure is decreased, the volume will increase the pressure. Decreasing the volume, will increase the pressure. So volume goes down, pressure goes up. When pressure decreases, the shift is towards more moles of gas. It wants more area for the gas. So, changes in concentration. When we have changes in concentration between the reactants and the products, if I add reactants, it'll shift it to the products. If I remove reactants, then the products will shift to the reactant side. If I add products, it'll shift back to the reactants. So I'm trying to always be equal. If I remove the products, which a lot of industry does, they work on building the product and then they pull the product out so it'll make more product. So it'll shift reactants to the products. A common ion effect, this is an example of adding a reactant or product to an equilibrium reaction that causes it to shift to the right or to the left. So I add a common thing that maybe is on the reactant side or on the product side and it makes it shift. Changes in reaction temperature can also shift a reaction. Remember we were working with delta H and we could put delta H into the reaction. Here it would be a negative delta H because it's on the product side. Okay, this is an exothermic reaction. If I add heat, that's like putting something in on the product side, it's going to shift to the reactant side. If I remove heat, that means take it out, that's going to shift the things to where I'm taking things out. So it'll shift to the right. If I change it as an endothermic, remember endothermic is a positive delta H. If I add, we'll do remove heat first. If I remove heat, it's going to shift my products to my reactants. If I add heat, put it in, it's going to shift it away from where I'm putting stuff in. And that's it. That's all you need to know about equilibrium. We'll work on it in class and we'll actually do a lab. So I hope you've figured it out.